First, I want to say that I'm sorry this took so long. Obviously, it took longer than I anticipated. I thought I was going to get this done by like last Friday, and then I thought it was going to be done Sunday night, and now it's the following Tuesday, almost Wednesday. You can see in the bottom right corner. But I think that all the time I took on it was worth it. This program is very nice. It's structured. It's very simple to add new code to make the Arduino do more things, and I think in the long run it's going to help us out more because it's going to help us better focus on writing code, getting code into the Arduino, and testing it to make sure it works, so that we spend less time on the programming part and more time on making sure that the machine actually works. This program here is the C++ program that will comprise the back end of our program, or one side of the serial interface. It'll mainly be receiving data from that serial interface in order to do what it needs to do so that the motors can be driven properly to do whatever it is that we need it to do. The front end, I haven't started working on it yet, but I'm thinking I'm going to start working on it soon. It's looking like it's going to be in Python because Python is a relatively simple language to pick up. It is also very versatile in that it can do a lot of different things, especially a lot of things that have to do with like drawing and image processing and things like that. So it's looking pretty promising. It could also be another C++ program, but I'm thinking Python's a way to go. This text editor here is Visual Studio Code. It's a lightweight text editor from Microsoft. I'm not trying to plug them because, they're not paying me to say anything like that. But I will say that it's a nice text editor. So if you have any questions about it, even if it's stuff like the theme, how it is I'm able to edit and verify and even upload Arduino code from this editor, or even just, programming in general, it doesn't necessarily have to be something to do with Visual Studio Code. I'll definitely be open to helping you. Just shoot me a message. It can be through the group chat. It can be through some other medium. You can email me. And even if it's something that we'll have to jump on a Zoom call for a couple of minutes for, I'll definitely be willing to help you out. So please don't hesitate to contact me. Next, we're going to talk about the main flow of this program. All of this is based on this command structure that I wrote. I'll go over the details of what's inside of it later on in the video, but this is the binding piece to pull this program together. It is my representation of taking that raw data from the serial buffer that the Arduino has and translating it into something usable for this program so that we can write and call descriptive methods that can still be translated into pretty robust instructions for our motor drivers so that we can drive them as we need to, and so we can make this machine work smoothly. When it comes to Arduino programs in general, every Arduino program is going to have these two functions right here. It's going to have a setup function, which is initialization code. That's where you're going to initialize everything that has to do with the program. So in this case, our XY plotter controller is going to call its initialize plotter method. That initialize plotter method basically starts a serial interface, and as we go on, if it's necessary, it will also initialize other values such as like speed values. Maybe once we start tinkering with like step measurements and things like that, we can make some sort of scalable value so that we can put it into the program and make things easier for us to understand. But that's basically what the initialize plotter method is going to do. Going back to the main program, once we set everything up, we're going to go into the loop function, which is going to make the command parser call its Q function. The Q function basically makes the command parser sit there and wait for a specified amount of serial data to sit in the serial buffer. It'll read all that data, and then it'll process it and return it as a command object, the same one that I described just a few minutes ago. After that, our plotter controller is going to take over again. It's going to take that command as an input, and it's going to execute it. After executing it, it's going to emit either an OK message or an error message. These functions are defined in this serial utility file that I wrote. It's only got two functions in it. There's send message and there's get message. Get message obviously getting raw data from the buffer, and send message obviously sending a message out into the serial interface. I also have a couple of string constants here that we can change, but I feel like it makes it easier for us to implement in the program because, I mean, you guys know why we use constants in programs. You can change it in one place and it changes everywhere. You don't have to go hunting down where you used it. So if for some reason, even if we wanted to change OK to OK, save it and it's not going to cause an issue. Alright, so it's a serial utility, the command parser. We basically went over that. I'm going to go into the details of how this is going to be implemented in just a minute. And also the XY plotter controller, I'll be doing the same thing. But just as a general overview, the command parser is taking raw data from the serial interface, converting it into a command, so that we can use it in the plotter controller class as an input to be able to execute that command. Upon execution, all the executable commands will be implemented as functions like this. In this case, I just have turn off because don't necessarily know what other functions we're going to need just yet, but I do know that we're going to have a way to, put the plotter in some sort of safe state. So I went ahead and put that in there just kind of as an example. All these functions are going to return booleans for whether they succeeded or failed. Upon success, this function will send a message that says OK to the front end program, and upon failure, it'll send a message that says something about an error. That lets the front end program know that it needs to either stop execution or needs to warn, put some sort of message on the screen that like, hey, something happened, this is not going to work. You need to go take a look at something. And then we can move on from there. But I think that's a pretty useful mechanism for us to be able to tell how well our machine is working. Moving on, going into the more in-depth stuff, going back to the main firmware program, this loop here is an infinite loop. I'm not sure how familiar all of you are with Arduino and the Arduino language. It's basically C++ with a couple of extra steps that Arduino put in. One of those steps is that this loop function loops forever until you power the Arduino off. And so the idea is to make kind of that call and response chain from the very beginning of the program. You set everything up. The initialization code is going to set everything up and send a ready message to the front end program. Front end program is going to send it a command. And this command parser is going to sit there and wait until that command is read. Once it's read, it fires. It goes through all the rest of this code, and then it queues again. It waits. That is the whole idea behind this program. It blocks, it waits, then as soon as it has enough data, it goes. Details of the serial utility class, there's not a whole lot to go over, except that it's very important that before you use the serial utility functions, that the serial interface is initialized. I say that just as a word of warning, but it's not really something that we're going to have to worry about because that initialization code is going to be taken care of in the initialize plotter function of the XY plotter controller class. Going back to command, I'll kind of give you some of the details about it. It has 3 fields. It has an instruction character array, basically a null terminated string. Once again, I'm not sure how familiar you guys are with programming and different styles of programming in different languages. But C style strings are actually just an array of characters that end with a null terminator character, which is why the max instruction length is 4, because each instruction has 4 characters, and that extra one is the null terminator character, and you have to be able to hold that. There's a field for the number of parameters that the instruction has. The biggest that I could think of that we would possibly need is 4, so that is 4 numbers, because the longest command that I can think of that we would have to implement is moving from one point to another point, that is giving the instruction 2 numbers to represent the first coordinate and then 2 numbers to represent the second coordinate. The way that I have this set up, though, is that each command is only going to have a maximum of 20 characters to represent it in raw data. That is 4 for the instruction, obviously, because it's 4 characters, and then 4 sets of 4 characters that represent numbers in hexadecimal. Hexadecimal is my way of, I think it's in command parser actually. Hexadecimal is my way of keeping all of the numbers consistent. Every number is going to be 4 characters long, but 4 characters allows us enough room to be able to expand those digits into however large we need to. For instance, 270F is 9,999 decimal, and I'm not sure that we're going to have to go much above that, but if we do, we definitely have the capability to, because obviously we have up to 9999 hex before we start having to expand the format of our data. Let's see, what else? The command parser, we're going to talk about a little bit of that implementation. Obviously, you're going to queue the command parser. This is the only public method, meaning it's the only method you're going to have to call, and that's because these 2 methods are fired in succession after this method is called. Once you call queue, it's going to call get raw data, which is the function that blocks and waits for the serial interface to get enough data to actually process into a command. It is then going to take that raw data into a character pointer and feed it into convert to command, and convert to command is going to convert it into one of those command structures I showed you earlier, filling in those characters and the number of parameters and all that kind of stuff. Once we're done processing the command, we're going to move on to the plotter controller, where the command will be executed. It's inputted into this execute command function, and what's going to happen is it's going to compare the instruction that's in the command to instruction constants that I defined in, I think it's command actually. I defined in the command header file, and based on what that instruction matches, it's going to execute and then send the corresponding message. The reason I implemented it this way is because if for some reason the instruction string doesn't match any of the instructions that we have, the result is already set to false. It's not going to change because it's never going to enter any if statements, and it's going to send an error message, which means we're going to have to check the format of the command that we sent through the serial interface. That pretty much wraps up the in-depth analysis of exactly what's going on here. Next, I will explain how exactly it is you can get this project on your computer and how you can start contributing to it and getting your code visible so that we can combine everything together. So if you take a look at this link that I'll have posted in the description, I've put all this code up on a GitHub page so that we can share it with one another, so that you guys can get it on your own computers and be able to write code for it, so that we can all see what's going on and we can all combine everything together. The way that sharing code through Git is going to work, though, is that I need the emails to you guys' GitHub accounts, assuming you have them. If you don't have them, you can get a GitHub Pro account through UGA, I'm pretty sure, if that is something that's important to you. Otherwise, GitHub accounts are free. Sign up for one real quick, make a username. It's just that easy. If you have any questions, I can help you out. Either way, if you can get me all of your emails, I can add you guys as collaborators to my project, and that way you guys can download my code and directly contribute to be able to push the code back up to this website so I can take a look at it, or so that we can all look at it together and decide how exactly we're going to merge all the code together into one cohesive program. So the first thing you need to do is to go to code here. Under clone, you should see 3 kind of categories of links. I would go to HTTPS, and I wouldn't really bother with the other 2. If you're really into SSH or maybe even the GitHub command line interface, I can go over that with you personally, but just for the low effort, easiest solution, copy the HTTPS link. That's the best way to go. Once you have that link, you're going to open a terminal. Obviously, if you have PowerShell, if you're on Windows, you're going to open that. Otherwise, you're just going to open a regular little terminal. I know Mac and Linux both use terminal emulators. You're going to fire that up. The first thing you need to do is make sure that you have Git installed. You have to have Git installed on your computer for this to work. If you don't have Git installed, a quick Google search will make that work out for you real nice. There's a Git for Windows. For Mac and Linux, there are separate but just as easy processes to get Git installed on your system so that you can do this. The other thing you're going to need is a text editor. I'm assuming that since all of you, I believe, have been in a class where you've had to program before, at some point you have some kind of text editor on your device. If you don't, or maybe if you're looking for a new text editor, again, I would recommend VS Code. But the main thing is just to make sure that you have a text editor on your device. Anyways, first thing you need to do is clone this repository to your computer. To do that, once you have Git installed, you're going to type in git clone, and then you're going to paste in that link that you got from that GitHub website. And optionally, you can pass in the name of the folder that you want it to be into. So you can see here, this is the list of folders that I have in this directory here. I call it cdev. Obviously, your code can be wherever you want. I already have an XY plotter folder, which is my actual active repository that this is based off of. So I'm going to actually put in an XY plotter 2 so that I don't mess with that. I'm going to clone it. And then you can go into that directory, take a look at the files that are in there. The first thing I want you to do is I want you to put in a git status. If it says on branch main and your branch is up to date with main, that's a good sign, but it is not time to start working on code yet. The reason is because we don't want to edit code directly on the main branch. That is because the code on the main branch has already been tested. We already know that it's been verified, that it will compile if it's on an Arduino, and that it works. Like, we don't have to worry about that. So what we're going to do is everybody actually has their own branch on GitHub. If you want to go back to the GitHub website, if you click on this branch button here, you should see you guys' names listed here. Mine's not here yet. I am going to end up making one for myself, obviously. But you guys have one here that you guys will be able to change into. So the first thing that I want you to do is find your name in this list, and you can not copy and paste it, but I'm sure you know what your name is. We're going to use Nick's branch for this example. So next step before you start typing in any code is you're going to do a git checkout Nick Bowring, not sure how you say it, but that's outside the scope of this video. Anyways, you're going to check out that repository. If you have been added as a collaborator and you're signed into GitHub on your system, which is also something that I can go over if you guys need help with that, then you will see the second line here that says that your branch is set up to track the remote branch of the same name from origin. Origin is the name of the source of this repository. It's the name of the remote. It's the place that you got it from. And that branch obviously matches the name of your branch. Once you do that, you're good to open your code editor and start making changes. Has already been tested. We already know that it's been verified, that it will compile if it's on an Arduino, and that it works. Like, we don't have to worry about that. So what we're going to do is everybody actually has their own branch on GitHub. If you want to go back to the GitHub website, if you click on this branch button here, you should see you guys' names listed here. Mine's not here yet. I am going to end up making one for myself, obviously. But you guys have one here that you guys will be able to change into. So the first thing that I want you to do is find your name in this list, and you can not copy and paste it, but I'm sure you know what your name is. We're going to use Nick's branch for this example. So next step before you start typing in any code is you're going to do a git checkout Nick Bowring, not sure how you say it, but that's outside the scope of this video. Anyways, you're going to check out that repository. If you have been added as a collaborator and you're signed into GitHub on your system, which is also something that I can go over if you guys need help with that, then you will see the second line here that says that your branch is set up to track the remote branch of the same name from origin. Origin is the name of the source of this repository. It's the name of the remote. It's the place that you got it from. And that branch obviously matches the name of your branch. Once you do that, you're good to open your code editor and start making changes. As it relates to making changes, though, I actually have a spreadsheet of functions that haven't been implemented yet. It looks like this. This link will also be in the description. It will also be on the repository's README once I update it with some information about the project. You guys will be able to click on it there so you can see the function that needs to be implemented. You can see if anybody's working on it, they'll have their name here, and you can see whether or not they're done. I will also be periodically checking this to see what functions have been done, what functions have been pushed up to GitHub, so that I know what we need to look at merging into the main program next. And as we come up with more functions that need to be implemented, they're going to go down this list too. So let's say that I actually want to make a change here. So I'm going to close this editor. I can open up my code editor VS Code through just the code command. So I can say code dot, that'll open up VS Code in the current directory. Obviously you would open up VS Code however it is not VS Code. You would open up your text editor however it is you would normally open up your text editor. I am very thankful that my text editor tells me which branch I'm on, so I can double check just to make sure I'm on Nick's branch. This is my branch. This is the one that I'll be editing, so that I don't try to edit the main branch, because once you save changes to the main branch, it's kind of a pain in the behind to make Git clean enough for you to be able to push the code up from your own branch, and you'll see what I mean if you make that mistake. But once again, I'm here to help you answer any questions that you might have. So let's say, for instance, no big changes, we're just going to change the README. So I'm going to add a line that says, this is a test. Save, boom. So we're going to go back to the terminal. We're going to run git status to see what our repository looks like. We say that we have modified the README file. As you can see, it gives you a little bit of hint. It says you need to git add the file to update what's going to be committed, which is the next step. We need to commit this. So in order to stage that commit or add a file to the files that are going to be committed, you would git add the README file. I'm trying to think. You git add the README file. If you have multiple files, obviously you would git add all of those files. A quick handy shortcut is git add dot, which adds all of the unadded files. Although you want to use that carefully, because if there are certain editor specific files, like I know VS Code generates a couple of files that it uses to be able to keep track of what's going on in your workspace, you don't want to add those, because you don't want to commit them to the actual public repository. The next step is, since you've added the file that needs to be changed, you're going to say git commit -m for message, because every commit needs a commit message. And we'll say, for instance, edited readme.md. Commit message formats aren't something that I'm going to take super seriously for this project, because it's a school project. This isn't professional code or anything like that. But obviously a clear descriptive message about what it is that you changed, what exactly you did. You could say implemented foo method in this class, and that could be your commit message. Anyways, once you have your commit message, hit commit. It'll give you a summary of your commit right here. If for some reason you didn't add the -m and the commit message, it'll open up your default text editor. Could be Notepad, could be something else, and it'll have you type the commit message in there. It's kind of a hassle if you don't know exactly how the flow of the process goes, though. So personally, I would just recommend that you always add that -m flag. It's going to be much easier that way. Next, in order to make our code public, if you're ready to make it public, if you made all your edits, you tested it out by yourself, you know that it's going to verify, it's going to compile, you can go ahead and git push. What that's going to do is going to push all of those changes up into the public branch that's on the internet. So that way, next time any of us logs in to go take a look at it, we can see that the branch, Nick's branch, had a recent change less than a minute ago. We can go take a look at Nick's branch and see what exactly happened. Then we can say, okay, well, he added the line, this is a test.